lesson on functions, and we're doing the reciprocal kind of function. So reciprocal function modeling, or reciprocal functions. So first of all, as well, let's recap so far. What type of function is each of these? So hopefully go back to the Firefly and watch the video on the first part of reciprocal functions. You'll see it's a video that I've gotten from YouTube, which is showing you lots of figures of people dancing and making these functions. So pause, and if you haven't watched that first, go back and watch that now. It's like how a mathematician dances. Then also, if it helps, you can kind of remember, like on page 3 and 4, like of your booklet, earlier in your booklet, I've kind of got examples of different functions, and you also filled in this part. So maybe flick back to your page 3 and 4 of your booklet, or whatever page it is, and look back and have a look at the functions, have a look at what you answered on this page as well. Then once you've paused and tried answering this, so then once you've done all that, try answering this yourself first, and then unpause and check your answers. So recap so far, hopefully you saw, what did you think this one was, this one, and this one. We've also given you clues down here, so hopefully you came up with these ones. Constant, linear, gradient 1, y-intercept 1, linear, gradient negative 1, y-intercept 1, quadratic, and it's got a positive a, so it's a smiley. This one's y equals 1, so it's a horizontal line. If it was x equals 1, it would be a vertical line. And try filling in these ones. Maybe pause. If you haven't done it already, try them out first. What kind are they? Now unpause and check your answers. So correct, the first one's a cubic. Cubic, it's an example of an x cubed. It's got a point of inflection right here. It doesn't have a vertex, doesn't have a maximum or a minimum. It has a point of inflection right here. Domain is XER, range is XER. Here we've got the absolute value. That means whatever x is, make it a positive. So it's kind of like, it's similar to y equals x, but notice that the negative values of x, they've just made into positive. So this part's the same, this arm's the same, but this arm has been turned up so that its y value is positive. Absolute value function. Here, if you just found the negative of that, it would just be flipped upside down. See, it looks similar to negative x, but the right arm, instead of being positive, it's been made negative because of the negative out the front here. And sine graphs are examples of trigonometric graphs. Next one, have a little look at these. Pause if you haven't done these already and try filling them in yourself. And then now unpause and check your answers. So first one, exponential. E is just a number. You might not have learned about E yet. It's a number like 2.7 blah blah blah, similar to pi, how it's an irrational number. So a number to the power of x, that's an exponential graph going whoop, up like that. lnx is the natural logarithm. It's an example of a logarithmic graph. It could have been just y equals log x. They kind of go up like that instead. Kind of like these. Exponential graphs and logarithmic graphs are inverses of each other. See how they're kind of reflected across the line y equals x. Next one, this was meant to be a constant, similar to the one above, but that one was y equals 1. This one's just, oops, yeah, actually, yeah, y equals 1, but this one is x is 0, so it should actually, instead of being like this, it should be going upwards. It would be a vertical line if it was x is 0. So let's just fix that. Rather than change the little diagram, you can try to change it, make the arms going up and like this and down like that. That's a bit hard to do though. So let's just change the function instead. The function should instead be y equals 0, because it's cutting the y-axis. It's a horizontal line. See, it's formed a horizontal line. So it cuts through the y-axis, not the x-axis. So it's y equals 0. Constant function still though. Next one, 1 over x is the topic of today's lesson. It's a reciprocal function, kind of going up. If you forget what that looks like. Reciprocal function, where is it? Here it is. Kind of going like that, kind of going like that. Pretty hard to do with your hands. That's why this one might have looked a bit confusing for you. 1 over x. Have a go what these ones are. Pause, try it yourself, then unpause and check your answers. Cos of x, just another example of a trigonometric graph. Finds these kind of waves, forms these kind of like sound wave looking things. X plus 1, it's a linear. It's got a gradient of 1 and a y-intercept of positive 1. So basically like y equals x, it's just been shifted up 1 unit. So that's why they're kind of standing upwards. They're kind of jumping up in the air. Because it's as if you were doing y equals x, this one here, but they jumped up 1 unit. So that's why this little figure's jumping up in the air. Whereas x minus 1 is just like y equals x, but it's just moved down a unit on the graph. So it's like y equals x as if they just crouch down a little bit. So the same gradient, it's just everything's just moved down a step. Y equals negative x squared, notice it's a negative quadratic. So if you want to kind of draw in the functions on the little dances, you can. So hopefully you got those answers correct. In the space below, draw a sketch of the reciprocal function and write out its general equation. See page 3 or 4 if you forgot. So let's have a look at 3 and 4. Reciprocal function. You could think of, so do a little sketch, dunk, dunk, and we're going to do dunk, and we're going to mark in asymptotes. They have a vertical asymptote and they also have a horizontal asymptote. And its general equation, sometimes people think of its general equation as y equals 1 over x, but even better, call it y equals k over x, because we don't know, there could be a number other than 1. It could be like 3 or 4 or negative 5. That's still possible. It's still a reciprocal function then. So let's do a dodgy sketch. Here we go. Here's an x-axis, no y-axis, here's an x-axis. You draw them kind of nice. Let's label them x and y. So I'm going to start to do that. X and y. And here we go. We've got our asymptotes we've got to draw. So this one has an asymptote, vertical asymptote going through here. What is the equation of this asymptote? It's x. It's not. Yes, it is. It's x equals 0. This asymptote going through here. Its equation is y equals 0. These asymptotes are not actually the function. They're parts where the function doesn't exist. So going back to here as well, what other aspects are there? We've got kind of two little bits that are the function. The function is this blue bit. It gets closer and closer to the asymptotes but never quite touches them. So it's going on infinitely that way and down here, going on infinitely. They're getting closer and closer to the asymptotes but they'll never touch them. That's just a thing that's special about these graphs. The general equation, remember, the general equation is y equals k over x. So the asymptotes are areas where the graph can't exist. So the function is actually in blue. So the function is in whatever colour you get. So in my case it's in blue. So the asymptotes are not part of the function. The asymptotes are in whatever colour you use, green. They are not part of the function. The function. So instead, they are areas where the functions cannot exist. The function cannot exist because in maths we cannot divide by what number? That's right, in maths we can't divide by 0. That looks like a road. Bio. We cannot divide by 0. Because see the general equation up here, I'll highlight in yellow. Here's the general equation. If x is 0, we get no solution. We get an error on our calculator. If x equals 0, we get an error as cannot divide by 0. So the reason why we have asymptotes, like areas where the function can't exist, is because at those areas, they're the parts where formerly you would have had x is 0 as a denominator, and we can't divide by 0. So hence why we have a vertical asymptote, and it's all because we cannot divide by 0. So there's a vertical asymptote because if you sub in x is 0 into this function that I've written, circled in yellow, into that equation, you would get an error on your calculator, because remember in maths we can't divide by 0. Why can't we divide by 0? Because formally dividing is asking us how many times do we subtract that number to get to 0. For example, 21 divided by 3 equals 7, because if you subtracted 3 from 21 7 times, you would get to 0. But 21 divided by 0 cannot do, because you can keep 21 minus 0 minus 0 minus 0, you'll never get to 0, it just stays 21. So that's why in maths you can't divide by 0, in case you were ever wondering. Cool. So we have vertical asymptotes at x equals 0, because if you subbed in x equals 0 into the function, you'll get an error. Why do we have a horizontal asymptote at y equals 0? We have a horizontal asymptote at y equals 0 because try to think. A number, k is just a number. A number divided by anything will not actually ever equal 0. Like a number, like say imagine k is 1. 1 divided by 3, it's not 0, it's a third. 1 divided by 100, it's not a 0, it's a hundredth. 1 divided by a million, it's getting closer to 0, but it's not equal to 0, it's a 1 millionth. 1 divided by 100 millionth, again it's getting closer to 0, but it never reaches 0. So what's 1 divided by negative 1? It's just negative 1. 1 divided by negative a million, it's like negative a millionth. You get closer and closer to the value of 0, y gets closer to 0, but it never actually will reach 0. So a number divided by any other number, you can never get 0. So that's why you get a horizontal asymptote. So we're going to talk right a bit about that down here. What are some features of this type of function? They contain, or they have, whatever, a vertical asymptote. So it's because we cannot divide by 0. So e.g. y equals 3 over x. If x equals 0, we get an error in our calculator. They also have, they contain a horizontal asymptote. They contain a horizontal asymptote because a number k divided by any number will never equal 0. For example, let's do the same function. So the same function as above, y equals 3 over x. So if x equals, for example, 2, then y equals 3 over 2. If x equals 200 million, then y equals 3 over 200 million. 200 so they don't get closer, it gets closer to 0, but never reaches 0. The value of y gets closer to 0, but never reaches. So therefore, we could say they have domain. Have a look at the little domain up here. Would you agree that the domain is every real number except for where the asymptote is? So any x value, it's because it's going off infinitely in that direction, it's going off infinitely in that direction. So it's every real number except for 0. How could you write that? This is just one way you could write it. You can write xer, except x is not allowed to equal 0. It's one way you could write it. Domain plus our range. Range, whoops. So range is kind of, where is it moving? Vertically. So it's going infinitely upwards this way, going infinitely downwards this way. But they can't equal any value where the horizontal asymptote is. So every real number for y except for 0, because of the horizontal asymptote. So yer except y cannot equal 0. Depends on your textbook and your curriculum. Some places are just happy if you just write y is not equal to 0, x is not equal to 0. Some books kind of like you to write xer, x is not equal to 0, yer, y is not equal to 0. So as I said, sometimes in some curriculums it's fine to just do this. So we'll just have to kind of look into past exams on CAE and see what they have ended up deciding, if they even ask you those kind of questions. So that's kind of generally what reciprocal functions are. You can think of anything else. They are functions because a vertical line test, would you agree, you would only ever cut the graph once. So that's what's kind of special about those. Can't think of anything else really cool right now. So trying to say, hang on, what is an asymptote? So as I said, an asymptote, it's not a function. The function is in blue. The asymptotes are the dot, dot, dot lines in green. So the function is actually not the part of the asymptote. The asymptotes are in green. They are not the function. Instead, they are areas where the function cannot exist. Because in maths we can't divide by 0 and so on, and also the reason for the horizontal asymptote. So what would be the equation of the reciprocal function below? Here it is. Try to think, where is the asymptote? So here's a little asymptote through here. What's the equation? It's y equals 2. So it's like the previous one on the previous page. Similar to that one that I've got in yellow, but instead of y equals k over x, that's y equals k over x, but then a plus 2 at the end, because everything got shifted up one. But wait, is it just that as well? We've got to check. Has it shifted sideways at all? It doesn't seem to have, because where's the vertical asymptote? The vertical asymptote's through here, and I think later in this page I ask you to write in the vertical asymptote and its equation. So I'll just do that now. That's going to help you. So you'll see an answer. X equals 0. That's the asymptote. The vertical asymptote and horizontal asymptote is y equals 2. So the function, therefore, would be similar to the one before. Y equals k over x. Maybe at this point let's just call it y equals 1 over x. Y equals 1 over x. It could have been a different value for it. That we don't have any coordinates to help us work out whether it's a 1 on the top or a 3 or a 2. So at this point let's maybe say 1 over x. But because everything got moved up 2 units, like the vertical asymptote, the horizontal asymptote it's not at y equals 0 anymore, it's shifted up to y equals 2. So we have a little plus 2, that just means it's shifted upwards. If everything had shifted down, we would have a minus 2 here. So let's make a note of that, as it's the same as the previous one, which was like, the general form 1 over x, but shifted up 2 units. Not sideways, but up 2 units. So that's where the 2 came from. And instead of shifting down, it shifted up. So that's why it's plus 2. Didn't shift sideways. If it shifted sideways, there would, don't write anything here, but if it shifted sideways, there'd be something here like +1 or -1. But it didn't shift sideways. It only shifted vertically. So that would be the general equation for that one. The graph below is missing a second asymptote. It was the vertical one. What would be the equation of this asymptote? So it's the horizontal one was already filled in, the vertical one, and draw the asymptote on the graph. So that's the second one we drew, which was the vertical one. Its equation was x equals 0, because it cuts through x equals 0 on the x-axis. So it would be just x equals 0 is the equation of that asymptote. The equation of the horizontal one was y equals 2, which is on the graph already. Yeah, we'll read it in the graph. What should be the equation? Okay, that one's done. Is the asymptote actually part of the function? So remember from the previous page? No, it's not. No, it's not. It's just an area of the graph, an area where the function does not exist. I know it seems weird to think of functions not existing, but it's all because we can't divide by 0. So the reason being is we cannot divide by 0. Plus also, a number divided by any number will never equal 0. That's why we have the vertical one as well. So is the asymptote actually part of the function? So let's go on to the next page. On the previous page, what does MC hammer say about the asymptote, the dotted line on the function? So what's MC hammer saying about that dotted line? You can see it here. So he's saying, can't touch this. So use the equation for the reciprocal function to explain why MC hammer says this. So the equation was this one, y equals 1 over x plus 2. So the equation was, let's write it again, y equals 1 over x, could have just been k over x, but let's just say it's 1 for now. Maybe it was 2 over x, maybe it's 3 over x, but let's just say it's 1, because we don't have a coordinate to be able to work out what that value of k is. So why does MC hammer say you can't touch this? So MC hammer is he's speaking to the function. So he's speaking to the function. He's saying that the function can get closer and closer to the asymptote. Whatever color you used, asymptote. But we'll never touch it. Touch or cross it. Very interesting concept in maths. So that's what they're saying. So it gets closer and closer. So what he's saying is, on here you can see that red function, sorry, the function in this case is in red. So here's the function. If you want, draw it in blue, whatever color you want your functions to be. Leave it red if you like. So you see the function, it's getting closer and closer to the asymptote. Going on forever this way. But it's never touching it. Same this way, it's getting closer and closer, but it never touches or crosses it. Here we go, this one. It's getting closer and closer this way, but never touching or crossing it. Just trying to scroll down here. And then keep seeing here, it's getting closer and closer to the vertical asymptote. It's never gonna cross it or touch it even. It's just a special new concept in math that you might never have seen before. The concept of the asymptote. And it's all because you can't divide by 0. Is a reason. So that little inconvenient fact is messing us up. So hence the joke. Remember, the joke is that there's one person who can divide by 0. It's Chuck Norris. So hence that's why he's telling MC Hammer Chuck Norris can touch the asymptote. Just because he has that superpower. Moving right along. Same thing again. For the diagram below, explain why the function never ends. Try to think where would be the asymptote on that function. This particular function, there'd be an asymptote going through here, a vertical one going through x equals 0. It also seems to be on this function. There's a horizontal one going through y equals 0. Where is the function? If you're having trouble seeing the function, it's just this thing here. Going up like this. It's also going up like this, going out that way. So the high fives, why the fun never ends. So it's because of the fact that the function will never touch the asymptote. The function will never touch or cross the asymptote. Cross the asymptote. Therefore, in theory, the high five will never happen. Will never happen. So that's why the fun never ends. They're infinitely trying to high five. We can have it if you want. They are infinitely in the process of trying to high five. Or critics. Another little one. What's going on in the following diagram? Where do you see asymptotes? Let's try to fill them in. Maybe use a little color code if you want. I'm tending to do my asymptotes in green. What's the equation of that asymptote? It's pretty hard to say. What's the equation of this asymptote? This asymptote is pretty obviously y equals 0. Cut through y equals 0. We don't know what coordinate that asymptote is. We can call it x equals Gandalf. Oops. Is that how you spell Gandalf? Yeah, we do. Gandalf. Hence why they've said the range is all real numbers, because here's the actual function. So let's try to sketch it a bit better than what they did. It's got a y-intercept, no problem. It's never touching the asymptote. It's never touching or crossing it. So they do say it's a bit sketchily. Theirs looks like it's actually touching it. It's kind of hard to draw it accurately. You just do the best you can. Make sure it doesn't kind of cross it. So that's our lovely little function. So he's saying you shall not pass, our handoff. So that's why they're saying the range is all real numbers. See that vertically it's all real numbers. It's going infinitely upwards, infinitely downwards. All real numbers, except y equals 0. They kind of got this around the wrong way, haven't they? They've said it the wrong way around. This is the range, and this is the domain. They got it wrong, because all real numbers, except x cannot equal Gandalf. So they're saying that the coordinate of x, where the vertical asymptote goes through is Gandalf, and y equals 0. So the range, if you want to, you could say all real numbers. So don't forget they said all real numbers, so you could go XER, all real numbers for that one. And for the range, it's YER, except when y cannot equal 0. That's what our range is. So they had it the wrong way around. Range, domain is all the x values, XER, x cannot equal Gandalf, y cannot equal 0. Here's Gandalf saying thou shalt not pass the asymptote. Thou shalt not pass the asymptote. So, next one. What's going on in the following diagram? Another analogy, so hopefully it helps you to understand. If you see these ones, we've kind of got functions again. Seem to have asymptotes going through here. It's hard to see this one exactly. An asymptote going through here. So x equals 0, y equals 0 for that asymptote. The function, they draw in red. If you want to color code it, draw it in blue. So infinitely this way, infinitely that one. And they're saying that the function in this case is y equals 1 over x. What they're trying to say here is, I'm really happy that we're closely approaching infinity and all. So it seems to be that the girl is the function. The girl is the function. Seems to be the case. So she's a happy little function, trotting along. And let's see. So he's saying we're getting infinitely closer. So he seems to be, you could call him maybe the x-axis, or you can call him the horizontal asymptote. I love you like one of my asymptotes, she's saying. So, meaning that they get closer and closer, but she's never going to get that close to him. She just gets closer to him, but not that close that she will fancy him. So instead of being friendship zone, he's being asymptote zone. That's why they're saying so close. So if you want, you can call the guy the asymptote if you want. I like you like one of my asymptotes. Mind you, she's got the asymptotes. So he's just kind of crawling along the asymptote. Girl is a function. The guy is like the x-axis, maybe you want to say, x-axis. She and he get closer over time, but never close enough. To be dated. So she's compared him to liking one of her asymptotes. I mean, she's never going to be closer enough to an asymptote. So never dating. So he has been friendship zone, or friend zone, by the function. So she said, I like you like your friend, basically. If that makes any sense, if that's confused you more, that's fine. Just ignore this page. And just keep moving along. Let's do some normal, regular examples. So find the equations for the following reciprocal functions. So first of all, let's have a look. What would be its asymptotes? Because the asymptotes will determine whether or not we need to add a plus something at the end, and whether we need any vertical, horizontal shift in there as well. So it seems to be this asymptote. It seems to be going through here. So it's y equals 0. And it seems to have the asymptote going through here as well. X equals 0. So there's no horizontal or vertical shift if you've just got x equals 0 and y equals 0. So no horizontal or vertical shift as asymptotes are x equals 0, y equals 0. So the general, it's just going to be part of the general function. General function, remember, is y equals k over x. But let's see, is k 1, is it 2, is it 3? It's a bit hard to tell. But we can use a coordinate. Let's use this coordinate right here. Coordinate is x is 1, y is 5. X, y. So let's sub it in. So when using 1 and 5, let's go 5 in place of y equals k over x, which is 1. So what's k going to equal? 5 times 1. So k equals 5. So our function therefore is y equals 5 over x. So notice how on the earlier example we weren't able to work out its equation because we didn't have a coordinate like the blue one I just plotted there to be able to do that. When we do have a coordinate, we can actually work out what the value of k is. This one was clearly drawn. There was points at 1 and 5, and I just knew that this was going to be the equation as well. There's no horizontal or vertical shift. So not having to, like, if there was vertical shift, you'd have to add or subtract here. If there was horizontal shift, we'd have to put something down here. Like, oh, goodness me. We'd have to put something down here, like -3 or +4 or something like that. So just don't do that. So instead, this is the answer here. Y equals 5 over x. Done. Next one, let's see, let's start with the asymptote. If they're not already marked in for you, make sure they're marked in. Seems to be 1 going through here at y equals 0. The horizontal one doesn't seem to be the x-axis this time. It seems to be, sorry, the vertical one. It seems to be going through here. So if you dot, 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 use a nice ruler to do this instead of what I'm doing. Where does it go through? It happens to go through x equals 1. So we can say there is horizontal shift and vertical asymptote is at x equals 1. The horizontal asymptote's at y equals 0, so there's no vertical shift. There's not been any shifting up or down. There's just been shifting 1 unit to the right. So to do that, you could say y equals k over x, but because it's been shifted 1 unit in the positive direction, we put -1 here. So this might mess with you. If it was a vertical shift, you would put +3. If it was +3, you would put -3 if it's down 3. But if it's horizontal shift, we have the sign is opposite. Opposite sign to the shift if horizontal. If it's a vertical shift, then it's like plus if it's going upwards, it's minus if it's going downwards. But if it's horizontal, it's the opposite sign to the shift. Now we need to check with a coordinate whether or not, like a good coordinate to use might be 2 and 1, what the value of k is. So we're going to use 2 and 1. X is 2, y is 1. I'm going to plug it in. 1 equals k over x minus 1. 2 minus 1. So 2 minus 1 is 1. So 1 times 1 is k, so k equals 1. So our function therefore is just, do it here, y equals 1 over x minus 1. That's our function. Because there was horizontal shift, 1 unit to the right. So this indicates as there was a horizontal shift shift 1 unit to the right. If it was a shift 1 unit to the left, it would have been x plus 1. So it's the opposite direction for horizontal shift. There was no vertical shift, so that's why there's not a plus something at the end or a minus something at the end. Let's have a look at this one. The asymptote's kind of been done already a little bit for you in a bit of a dodgy colour, a dodgy line. Let's draw over it again with dot dot dots, make it look more asymptote-y. So we've got a vertical one. Again, remember asymptotes are regions where the function can't exist. Where does it cut through? It seems to cut through x equals 2. according to the scale. Here's the horizontal one. Where does it cut through? Y equals to 6, so it must be a 4. And the function's just been drawn in blue, kind of roughly. Sorry, messy. Excuse me. So the general form, y equals, we might be able to work out k. See, I might be able to use something to work out k, hopefully. So we've got k over, so because there was some horizontal shift, and it was 2 units in the positive direction. So 2 units to the right, so it's x minus 2. Because the horizontal shift, 2 units to the right. Remember, vertical shift kind of comes at the end and it matches the sign. So it's shifted 4 units upwards. So it's plus 4. And then we might be able to work out k, but I'll just write a little note of why that is. As there was vertical shift, 4 units in the positive vertical direction, which is upwards. This one is as there was horizontal shift. Shift 2 units to the right. So identifying the asymptotes was crucial in identifying the shift. Because remember, the general version, y equals k over x, the asymptotes at x equals 0 and y equals 0. So identifying the asymptotes enables us to kind of like find that out. So what you could do is do we have a coordinate that we could actually use on the graph? So could we use the y-intercept? We probably could. So we can use the y-intercept. Let's use that. We're going to use the y-intercept as our coordinate. So coordinate is going to be the y-intercept, which is 0. We don't know what it is though, that's kind of annoying. So it's kind of, let's say 0, and what can we say it is? Look, it looks like it's about a third of the way down to 2. So a third of the way down to 2 is kind of like 2/3, maybe. Kind of awkward. Let's just say it is 2/3. So y equals negative 2/3, isn't it? Negative 2/3. So now we've got to try subbing that in. Doesn't seem to want to scroll down. Let's do it sometime. Okay, so I have to do this on my laptop. There we go. So now I'm going to plug in x and y. So that's our x. This is our y. And maybe I'll do it down here. So let's do that down here a bit, so you can see it. So y is negative 2/3. Let's plug that in. Negative 2/3 equals, we don't know what k is at this point, k over x is 0. 0 minus 2, and then don't forget you've got plus 4 going on there. So this is going to be awkward. So it's a shame that negative 2/3 isn't a whole number. Now we've got to start to rearrange and solve for k. So what's negative 2/3 minus 4? Let's do that. Negative 2/3, because it was plus 4, so minus 4 equals k over negative 2. 0 minus 2 is just negative 2. 2/3 minus 4. 2/3 is the same as if you, just use negative 2/3. But as a third, 4, would you agree it's the same as 12/3? Because k over negative 2. So negative 2/3 minus 12/3 is negative 14/3. Equals k over negative 2. You could cross multiply now if you want. No? Okay. Cross multiply. So cross multiply. Normally you wouldn't get something like 2/3, so just be a simple sloppy one. Negative 2 times negative 14 is 28. 3 times k, 3k. So 28 over 28 over 3 equals k. So our function is really awkward. So our function is going to be y equals, just see I'm going back to what was here, k, which you could write if you want as 28 over 3, normally it's a nice whole number, it's a pretty advanced one, 3 over, don't forget the other stuff, x minus 2 plus 4. X minus 2 plus 4, you could potentially rewrite this, so you could write it as y equals 28. Remember dividing, it's like putting it in there, that, but it's that times x minus 2. This is a pretty advanced one. It's hard, of course. And it's all because of the x coordinate. The coordinate kind of wasn't a nice whole number, so that's why we've got kind of the fractions going on. Good to see an example of a difficult one, I guess. Okay, example, use technology to graph the following reciprocal functions and find the equations of any asymptotes. You might want to do a basic kind of x and y axis to begin with. So get your little ruler out to your x-axis, vaguely, y-axis, x-axis, whatever order you want. Maybe I'll shift that up a bit. And they want us to find the equations of any asymptotes. You can probably have a look at this and have a little guess what the asymptotes are going to be. Because before, we had asymptotes, for this one, we had asymptotes at y equals 4 and x equals 2. So see, the y equals 4 came from here, and the x equals positive 2 came from here. So this would kind of help you work out what the asymptote, the vertical asymptote is, and it's all because it's an asymptote at x equals 2, because 2 minus 2 makes the denominator 0, which is not allowed in maths. And this one helps you to work out that. So that little negative 2, so we're going to have a, let's see, it's going to be a horizontal asymptote at y equals negative 2. And that's because there's no value of x is ever going to make this equal 0. That's why. Because 1 divided by any number at all gets closer and closer to 0, it never touches it. So that's why there's an asymptote of y equals negative 2. Because no matter what number you plug in for x, you're never going to get 0 as this being this answer, which means you'll never get negative 2 as the answer. And so we've got a vertical. We have a vertical asymptote. Here, but it's the opposite sign. X equals positive 1. Remember, it's the opposite. That's going to help. Maybe do it on technology now and just have a little look. So we're guessing there's going to be horizontal asymptote at y equals negative 2. Maybe I'll just put in a few little scales. That might be helpful. Let's have a look. 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 1, negative 2, negative 3, negative 4, negative 5. Very difficult to draw evenly on these boards, sorry, so please make sure yours is a lot more even than this. Negative 4. Don't forget to label x and y axis. So let's mark in our asymptotes if you want. Use a ruler, please. Horizontal asymptote at y equals negative 2. Y equals negative 2 down here. It can be good to draw your asymptotes first. We have a vertical asymptote at x equals 1. X equals 1 will be going through here. According to our scale. Make sure to label your asymptotes. X equals 1. Now you can probably guess that the graph's kind of going to be doing this and that, but if you're not sure, just have a little graph of it and calculator. So let's do that. It's 1 over x minus 1 minus 2. Let's go, remember you go on the Inspire, open up a graph. So you could use a nice fraction. You can make a nice fraction if you want. So it was 1 over x minus 2, no, x minus 1. X minus 1 minus 2. Double check have I got the right one. 1 over x minus 1 minus 2, that's it. Enter. If you want to double check your axes, maybe I'll make my negative 4 to 4 in the x and negative 5 to 5, negative 4 to 4. So let's go menu. This is a helpful thing to know, how to adjust your window settings if you don't already. X min, negative 4, X max, positive 4. So negative 4, positive 4. Awesome. Y min, negative 5 up to positive 5. So then you kind of have it roughly to the same scale as what you've drawn out. There it is, cool. It doesn't give you the asymptotes on here, which is a bit annoying. Let's see, does it ever? I don't think it does. But what you can always do is, if you're not sure of the asymptotes, you can trace. Actually, I'm just going to sketch this first. Let's do a quick sketch. Just escape to get out of there. Let's quickly sketch it so you can see it does go down like that. It crosses a y-axis. So if you could find that y-intercept, the y value of the y-intercept there, like that kind of thing. And you can kind of find it here. Maybe we should do that. Okay, let's find its x-intercept and its y-intercept. So let's go to tracing. Menu, trace, just so I can be nice. Graph trace and nice and accurate. So it's, what's its x-intercept? It's got an x-intercept at, there you go, 0, what's that? Negative 3. So it seems to have an, yeah, because that's this one down here. 0, negative 3, let's plot that little point. 0, negative 3, right there. And now let's work out its x-intercept. So keep tracing, keep going to the right, and you'll see what value of x is it getting closer and closer to. See how it's getting closer and closer to, oh yeah, but you might think that it's crossed 1. Yes, it has. No, see, it's jumped from being up really high to being low. So when you're here, you're going further and further down this way, and then suddenly it jumps to being up here. So that's what's going on. You'll sort of see. Yep. So once you're past 1 and here, means you're past the asymptote, and you're up here now. Because see, the y value is now suddenly really high. Whereas before, oh, see, there you go. It does tell us the asymptote. So if you keep tracing, see where it says 1 undefined. That means you're at the asymptote. Great. So the TI Inspire does point out where the asymptote is, because it's telling you that y is undefined at x equals 1. Cool. So now I just want to find where's the x-intercept going to be. We found the y-intercept. So remember, keep tracing till it says 0. I'm just going to go back here a bit because I couldn't see the coordinate. Now I'm going to go back to the x-intercept. So when it pops up and says 0, our x-intercept is at, is that 1.5 or is that 15? Just 1 second. Okay, it does look like 15 on here, but I can confirm for you that it is 1.5. It's just really small on the screen. So it should be at 1.5. So here's 1, here's 2, 1.5 is right here. There you go. And then once you've got your little x and y intercepts kind of in roughly where they should be, you can draw your dodgy looking graph. So it's kind of going kind of like here. If you want, you can put your little arrows on. Going down here, it doesn't cross the asymptote. Make sure it doesn't cross the asymptote. It's kind of going down infinitely that way. Nice, that's our function. I think we're done. Yep. So we just found that there was a x-intercept at x equals 1.5. We found the y-intercept at y equals negative 3. We found that one by just tracing. Now let's do another practice one below just to make sure we've got the hang of it, and then we'll finally be done with this lesson. So very similar one. This time we've got y equals 1 over x plus 2 plus 1. So let's draw in our axes again. thing. So we can tell where our asymptotes are going to be. So it's going to help us for being able to draw. The asymptotes aren't going to be too far up and down because there's +1, +2. So you can kind of have a similar scale to before if you want. X, Y, go along 1, 2, 3, 4, 5 if you want. -1, -2, -3, -4, -5. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. You can put in more, so long as you've labelled somewhere on the scale, like somewhere that kind of looks nice and even like this. So let's remind ourselves how we find the asymptotes. So the horizontal asymptote came from this number here. The vertical asymptote came from that number there. Because the horizontal asymptote is y equals something. So what value of y is impossible? So it helps do vertical asymptote first. Let's do the vertical asymptote first. Because remember, the whole idea of these was more about what value of x is not possible. So what value of x is going to make the denominator equal to 0? So if x plus 2 equals 0, the value of x equals -2, because -2 plus 2 would make the denominator 0. So vertical asymptote at x equals -2. That's why we have to change the sign here. And we have horizontal asymptote. Because this part, in theory, will never equal 0, because you can plug in a million into that thing for x and you'll never get that fraction equaling 0. So therefore, 0 plus 1 is never possible. So horizontal asymptote at y equals +1. Let's do that. Y equals +1. Please use a ruler. And horizontal asymptote, sorry, vertical asymptote at x equals -2. X equals -2. Again, you can probably guess it's kind of going to go zhunk, and it's going to go zhunk. But maybe we can at least work out what is the exact value of the y-intercept. We might also be able to find out what is an x-intercept. So let's see if that's possible. Maybe the x-intercept's out here somewhere though, in which case we couldn't plot it. So let's try just doing a general sketch and adjusting the window so it looks similar to what we've got on the graph. Groovy. Right, let's do a new one. So make a fraction. So control to make the fraction. 1 over x plus 2. Jump out of the fraction and then +1. Okay, did it. Now let's maybe adjust the window a little bit and see whether or not we can actually see the x and y intercepts. So menu, window zoom, window settings. We want -5 to 5 for this one. So -5 up to 5. And then we want that should be -5 there, sorry. -5 up to 5. So it's going to look roughly like this. So it looks like on this axis we are going to see the y-intercept, of course, which we probably realised. We are actually going to see the x-intercept as well, though. And then, so let's trace along. Mix up this too. I should have -5 here. So that's a -5. If you want to rewrite it. -5. So we've got to work out where is our x-intercept. Which one? So to do that, remember you go menu, trace. Sorry, go back again. Menu, trace. I just do graph trace. Okay, y-intercept. Why not? Let's find that first. Y-intercept. Just be nice and accurate. Yeah, there it is. It's at 0 and 1.5. That looks like 15 on this screen, sorry, but it's 1.5. So we have a little y-intercept here. There's 2, there's 1. Hopefully your scale's a lot better than mine. So I told you I can't draw them very well on this board. Then keep tracing along. It's going to also point out that your asymptote's at -2. There you go. See, it told us -2, undefined. Yep, so that's confirmed our asymptote. We're going to go up and try to find where the x-axis, the x-intercept is now. So when it hits the x-intercept, the word 0 pops up. There you go, 0. If you didn't miss that, do it again. 0. 0 is at -3 on the x. So -1, -2, -3. You can always find that manually. Remember, at the x-intercept, y is 0, so you can plug in 0 and then rearrange and solve for x. That'll give you -3. To find the y-intercept, you plug in x is 0, so you can just substitute in 0 and you'll find that this ends up equaling 1.5. So now let's make our little dodgy graph. Let's draw the actual function now. And it's the function, it's going infinitely that way. Make sure it goes through your y-intercept. Kind of going down infinitely that way. And this one's kind of going down like that. Put the arrows on if you want to show what's going on. So we've got our x-intercept. That's x equals -3. We've got a y-intercept at y equals 1.5, which we found by tracing, but you could always do it by plugging in x is 0 and y is 0. So, oh goodness me, that was a long lesson. So thank you for your patience. Oh, no, we're not done. Great. Okay, so Kate has made 40 invitations for a birthday party. How can she make the invitations? How fast she can make the invitations will affect how long the job takes her. Great. Suppose Kate can make n invitations per hour, and the job takes her t hours. So this is the number of invitations per hour. She needs to make 40. So if she can make 4 invitations per hour, and she needs to make 40 in total, how many hours is it going to take her? So try to think, 4 per hour, it's going to take her 10 hours, because 10 times 4 will make 40. If she can make 8 invitations per hour, and she needs to make 40 invitations, how many hours will that take her? 8 times 5 will give her 40. If she can make 12 invitations per hour, how many is that going to take her? It's going to take her 40 divided by 12. If you're not sure what that is, you can divide the top and bottom by 4, if it helps, if you do it non-calc. Divide the top and bottom by 4, we've got 10 over 3. So 10 over 3 hours. Writing like this. 10 over 3 hours or 3 1/3. So 3 1/3 hours. And then complete the table of values. We've kind of done some vague ones here. 4, 8, 12. Could do another one if you want. You can do 20 if it helps. Why not? Let's do 20. So she can do 20 per hour. How many hours would it take her? It would only take her 2 hours. Seems to be a general function, doesn't it? Seems to be the time taken is equal to time taken is equal to 40 over n. Seems to be our general function, but let's see what happens. Draw a graph of n versus t with n on the horizontal axis. Just do it, so feel free to do it yourself. Just letting you know how it's going to look. I'm being lazy now because I stole this from an extra thing in the textbook. Where are we? Here we go. That was this one. There it is. It's going to end up looking like this. So you could do a big table of values. If you do a big table of values, you'll end up with that. There you go. Oh, great. Why did that happen? Big table of values is going to end up looking like that. See 3.3 recurring, or 10 at 3 1/3. Draw the graph. When you draw the graph, feel free to pause and draw it. When you draw the graph, it's going to end up looking like this, roughly. Okay. Let's draw this down here. So see, because like we have the n going along this way, like the x, and the y going up this way, which is the t. So first coordinate, 4 and 10. next coordinate 8 and 5, and so on. They went all the way up to 28. Then what you're asked to do, is it reasonable to draw a smooth curve through the points plotted in B? And what shape is the curve? Let's see. Yes, one part of a hyperbola. So basically reciprocal functions, like you know how quadratic functions are called parabolas, reciprocal functions are called hyperbolae. So this is one part of a hyperbola. Hyperbola is like, that's a hyperbola. Hyperbolic, they're called hyperbolic kind of graphs. Like, as I said, quadratics, another name for the actual shape is called a it's called a parabola. So reciprocal functions, they have their graphs, the shapes of their graphs have particular names. They're called hyperbolas. Hyperbola. You could do it. So you can draw a nice smooth curve. There you go. It's getting closer and closer to 0, but it's not quite touching it. So we seem to have asymptotes going on. And then we're asked, of course, state a formula for the relationship between n and t. So I said t equals 40 divided by n, because it's y equals something to do with x. So to get y, we had to do 40, the number of invitations, divided by 4, gave us 10. 40 divided by 8 gave us that, and so on. So this little thing, baby here, t equals 40 over n, gives us that. So it's already a long lesson, that's why I'm rushing through this. There you go. And finally, yep, we're done. Thank you so much for your patience.